Okay, so good evening. I'm going to go over the quiz 2 that we did. This is purposely for the quiz 2. So I go over briefly the questions that we did for quiz 2 so that you can get a bit of an understanding to prepare for your exams as well. The first question had to do with the properties of rational numbers. So we did say the properties of rational numbers. We did say that if we have a over b, we could represent it as a brackets square bracket a comma b. So really, it's nothing strange. And all the properties of rational numbers that we know from the basics carry through. So some of them is if you have the square bracket p comma q, it is equal to the square bracket a p comma aq. I mean, this is true because p over q is equal to a scalar of p and then the same scalar of q, which is p of q. So this is true. However, not all in the questions you saw that, for instance, if we had minus square bracket s of p, then this we should write it as minus s over p, and this is not the same as minus s over minus p, because minus s over minus p, we write it as minus s over minus p in such a format. Okay, and of course, this is the same as S of P, right? So this was really the exception out of those properties that were stated in the questions. And the other question was to find the number of solutions of a linear congruence. And there are many ways to solve this, but a quick way of solving or going about this is a clear-cut understanding of the greatest common divisor, using the greatest common divisor. So if you are given the number of solutions for 7x modulus is equal to 13 modulus 100, what you need to do is you take the number here, 7, the GCD of the number here, and the modulus. So if you take the GCD of 7 and 100 is equal to 1, we know that the GCD of 7 and 100 is 1, and that means that there's only one solution to this problem. Okay, so some examples are if you are given 66 of x is equal to 100 modulus 1, 2, 1, then you find the GCD of 66 and 1, 2, 1, and then if you realize that the GCD of 66 and 1, 2, 1 is 11, and now you check if this GCD, right, this GCD divides your 100, right, here. In this case, this 100 here. If it divides, then you know that there are a certain number of solutions. But if it does not, then you say that there are no solutions, right? So there are no solutions because the GCD does not divide this 100 that we have here. So I say another example is if you have 21 of x is equal to 14 modulo 91, the GCD of this 21, right, of 21 here, and then 91, the GCD is 7. Then we say that this GCD 7 here divides, right, divides. So this GCD 7 here divides 14. This 14 comes from here, right? And because it divides 14, we say that there are existing solutions to this linear congruence. So this is a way to determine if there are solutions or how many solutions there exist, or there are no solutions to a certain linear congruence. Okay. Then we go to finding In this case, you want to find the factorization of 2024 and 1984. Of course, this if you want to find the factorization of something like a number 2024, you have to really look for the prime factors of that number. And the way to do it is popularly what we used to do when we were in primary schools is something called like the factor tree. But the factor tree has limitations. So this we just discussed it as well. So you try to look for numbers that can divide this number so you are left with only primes, right? Only primes only. If you are left with primes only, then you know that that is what gives you. So this two is really it wasn't really complicated one. Then we also spoke about finding if you are given the GCD of two numbers. Here we have 78 and 106, 102. The GCD is 6. And then we are asked to find linear combinations of 102 times A plus 78 times B, which gives you 6, and to find this A and B. Okay, so what we said was here you can apply this Euclidean algorithm. You have 102 and 78. You can write 102 as 78 times 1 plus 24. Then now you come 78, you take your 24, and then now you write your 78 to be equal to 24 times a certain factor plus a certain factor. This is 24 times 3 plus 6. And now you take your 24, you take your 6, then you say that 24 is also 6 times 4 plus 0. So once you reach this part where this is 0, then you know that your GCD of 102 and 78 really, right, is 6, is this one here. Okay, and now what we want to do is we want to write this GCD, which is 6, as a linear combination of this 102 and 78 times some scalars. So we start with 6, and then we usually start with the last but one line here, right? We usually start with this line here, is where we start from. Then we say that you can write 6, the GCD 6, you can write it as 78 minus 24 times 3. And then your 24, now we go to the second line, you can write 24 as a combination of 102 and 78. So we replace 24 now by this combination, and then the 3 still remains. If we do that now, we can multiply through and factor out. If we do this, we have 78 times 4 plus 102 times minus 3. And this gives us what we are looking for. 102 times A plus 78 times B should give us 6. So we're able to now determine this A and B in such a manner. Next is we ask the question of relatively prime numbers, and of course this is the definition. Relatively prime means that the GCD of when two numbers are relatively prime, then their GCD is 1. So if we are asked to find a relatively prime number of 25, then you need to look for the numbers there such that the GCD of those two numbers gives you a 1. And so here we're given 25. So we look for all the numbers there such that they give you this, they together with 25 give you a GCD of 1. Then the next question was to ask, we were asked to solve was to find the residue class of modulo 5. So if you know how to find the residue class of modulo 5, you know that it is simply if you have 0, then you need to find all the entries here such that they can divide. It is divisible by 5, or it is divisible by 5, and then you get an integer. Okay, you get an integer, or you get a residue in that manner as well. Right, so we said that if you have this residue class, it just means you have n minus 0 over 5. And then now we know that it should be an integer, so we need to find all such n, right? Find all such n which are also integers. So for instance, if we take this, we take the 0, the residue 0, residue class 0, we know that if n is minus 10, so for instance, here we can have minus 5 minus 0 over 5 is equal to minus 5, and this is equal to minus 1, right? Is equal to minus 1, and this is an integer as well. So we look for only integers, and in that sense, we're able to create a residue class. So for 0, we can write it. For 1, we can write n minus 1 over 5 to be integer. So we need to look for all the entries n, such that n minus 1 over 5 will still give us integers. If we come here, you see we have, for instance, here we have 1. You understand that if you have 1 minus 1 over 5, this is 0, and this is an integer. That is why 1 is here. Okay, and so on. So if we do that, because we are in modulo 5, we know that we need residue class 0, residue class 1, up to residue class 4. Okay, and then you shouldn't forget what we said about some properties of the residue class. When we spoke about the residue class, we said the residue class creates partitions, and the union of all the residue classes, okay, will give us the whole set. So these are properties you shouldn't also forget. And so you see that if we take, for instance, this residue class, in this case, we can see that we can create the whole set Z if we just take the residue, residue class 0, union 1, union 2, up to union 4. It will create the whole set Z, number system Z for us. Okay. Okay. Then next, we did ask questions on prime number theorem. Okay, prime number theorem. So this we give a formula for prime number theorem. This is the formula for prime number theorem. So for prime number theorem, we give a formula, and we said that if you write pi of x is approximately equal to x over ln x, and that is the prime number theorem. So here we chose x to be 10 to the power 3. So this is pi of 10 to the power 3 is approximately 10 to the power 3 over ln 10 to the power 3. And this is equal to 144.76, which is approximately 145. So it doesn't matter if I give you x to be 2 times 10 to the power 3. All you have to do is you find times 10 to the power 3, right? It's approximately 2 times 10 to the power 3 over ln of 2 times 10 to the power 3. So this is how you find these numbers. Of course, usually I approximate them, I round them up. So okay, then the next one was the Mersenne prime. So we said that the Mersenne prime is a prime number which is following such a formula: MP is equal to 2 to the power p minus 1, where p is prime and MP will also be prime. So if P is prime and MP is also prime, then we say that this MP is a Mersenne prime. So it's not really a tricky question, but it's just an understanding of what this means. So here you see that if we take, for instance, all the prime numbers 2, 3, 5, 7, 11, 13, if we take use the same formula here, MP is equal to 2 to the power p minus 1. If we take p to be 2, we'll get 3. And 3 is also a prime number. So we say that 3 is also a Mersenne prime. Okay? If we take 3, which is a prime number 3, we will get here, okay? We'll get here, we'll get 7. And 7 is also a prime number. So it is a Mersenne prime. It follows the formula 2 to the power p minus 1. And then if we take 5, we have 31. So 31 is a prime number and 5 is a prime number. So we have a Mersenne prime 31. If we take 7, we have 127. This is a prime number. So we say that it is a Mersenne prime. It follows the formula. But if we take 11, we will see that 11, if we put p is equal to 11 in this formula, we will get 2047. And we realize that 2047 is not a prime number. So 2047, right, is equal to 23 times 89. So it is not a prime number, right? So in that case, although this is a prime number p, the resultant here, which is 2047, is not a prime number. So it is not a Mersenne prime. So this one is not, does not qualify, right? It's not, because it is not a prime number. So there are many numbers you can generate from this using p to be prime, but not all of them will end up giving you MP, which is also a prime number. Those ones which end up with MP also as prime number, we call that a Mersenne prime. Okay, so then the next one was to find the inverse of 7 modulus 26. So you can write such a write such a statement as 7x is equal to 1 in modulo 26, and this you can write it as 7x is equal to 1 plus 26m, where now your x is equal to 1 plus 26m over 7. So if you do that, and then you take m, for every m, you can put, for every m, you can check what x will be, right? So here, of course, you shouldn't forget, we are looking for x, such that x, we are looking for x, such that x is also an integer, okay? So that x is also an integer. So here, we draw a table, we put m to be 0, then we calculate for x, we get 1 over 7. We put m to be 1, we get 27 over 7, and so on until we put m to be 4, and then immediately we get 15. So in that sense, we say that if we put 4 here, we'll get 15, and so 15 will be the inverse of 7 in modulo 26. Then the next one was to find was something in the sense of complex numbers of nth, okay, of nth order. So we're given 2 cos pi over 6 plus I sine pi over 6 all to the power 8, and we're told to find the complex values in the complex domain coordinate system, right? Complex coordinates. So we use the formula that we know that if we want to find at the nth root, then we know the n power, then we know Rn is equal to cos n theta plus I sine n theta. Okay, plus sine n theta. Okay, so in that sense, if we write here, then what we do is that we know that we are dealing with n is equal to 8, And then our theta, we know is pi over 6. So we can rewrite now our equation in terms of this formula here. So z of 8 is nothing but 2 to the power 8 cos 8 times now the theta here is pi over 6 plus I sine 8 times the theta, which is pi over 6. 8 to the power 2 to the power 8 is 256. Then now cos 8 times pi over 6, which is like 240 degrees, happens here in this bracket where it is minus x and minus y. Okay, you come here, and then this is 8 pi over 6. Okay, 8 pi over 6. So if you do that, then you know that you have a 60-degree angle here, or pi over here, you have a 60-degree angle here. That gives us minus half. And then, of course, as well, on the sine direction, it gives us minus square root of 3 over 2. So if you multiply through, then you have minus 128 minus 128 square root of 3 of I. That's solution in complex. The next question was to find the maximum value of x, such that x is between 100 and 200. Satisfy the linear form where x is equal to 63 in modulus 32. Of course, x is equal to 63 modulo 32 can be written as x is equal to 63 plus 32m, where m is an integer. So all we do is I draw a table of m and x. If I put m to be 0, I have 63. If I put m to be 1, I have 95. If I put m to be 2, I have 129, 127. If I put m to be 3, I have 159. If I put m to be 4, I have 191. Of course, then it means that if I put m to be 5, I'm already out of bounds because it is going to be 32 times 5 plus 63, and this is going to be 223. So I'm already out of bounds. So the maximum value for x is really 191 in this case. Then, of course, the next one was the Chinese remainder theorem application. Here, we are given a question that x is equal to 5 in modulo 25 and x is equal to 32 modulo 23. So what do? Here we know A1 is this value here, A1, and then A2 is this value here, 32. A1 is 5, A2 is 32. And N1 is this value here, which is 25, and N2 is this value here, 23. Then we create as a product of the modulus. So we call it a big N, which is now the modulus N1 and the modulus M2 multiplying together to give us 575. Then the next thing we do is that we calculate these values here. We calculate this capital N1, capital N2. So capital N1 is nothing but this big N over the small n1. That gives us the capital N1, which is here 23. And then we do capital N2, which is now the big N again over N2, the modulus N2. And then this is also 25. Then the next thing is we calculate the multiplicative inverse of these modulus. So of modulus N1, the big N1, and then also of the big N2. So if we have the N1, the big N1 is 23, right? And then the big N2 is so we we find the multiplicative inverse of n1 and then the multiplicative inverse of n2, the big N1 and the big N2, capital N1, capital N2. So to find the multiplicative inverse of N1 of 23, N1 is 23, capital N1 is 23, its multiplicative inverse is 12. And then capital N2, which is 25, its multiplicative inverse as well is 12. So once we have that, then we can write now, follow formula A1, N1, A1 times N1 times the multiplicative inverse of N1 plus A2 times N2 times the multiplicative inverse of N2 in a big modulo N. So if you follow that, then you will see that A1 here is 5, N1 is 23, and multiplicative inverse of N1 is 12 plus here, so we have A2 is 32, N2 is 25, and its multiplicative inverse is 12. If we do that and we sum, we'll get 10, 9, 8. And this, of course, will be in modulo 575. So when we have this, so it means that we have x is equal to 10, 980 modulo 575. And this is the same as x, and this is the same as x is equal to, this is the same as x is equal to 55 modulo 575. And this gives us, we can write this now as this, and then this gives us our final solution. Of course, you'll be wondering, why is x equal to, why is x 10, 980 modulus 575, right? The same as or equal to x 55 modulus 575. It's really not a difficult thing, because if we take 10, 980 and we divide by 575, we realize that there is a remainder of 55, and that actually means that they are equivalent. You can write them as equal, or is the same, or is equal to. So we can write also this equation, and that finally gives us the right result. Then next, we did talk about the complex numbers. So here we are given 1 over 2 plus 2i, and we are asked to find or write it in an exponential form. So in for such a problem, what you do is, of course, you need to multiply this by the conjugate, both by the numerator and the denominator, the conjugate. And then if you do multiply by the conjugate, you multiply through, then you get 2 minus 2i over 8. And this is equal to 1 over 4 minus 1 over 4i. And once you have this, which is your x plus iy, now you can write the modulus. The modulus, which is the square root of 1 over 4 squared plus the square root of minus 1 over 4 squared. And this is square root of 2 over 4. And now we can find the angle theta. The theta is nothing but the tan inverse of x over y, or you can say it's y over x, or you can say b over a, whichever way you want to call it. And this really means it's minus 1 over 4 over 1 over 4, the tan inverse of that, and that gives us the tan inverse of minus 1, which is equal to minus pi over 4. And this, now we can write z in a exponential form, which usually looks like that, by theta of I. So in our case, our R is square root of 2 over 4, and then our theta is minus pi over 4 of I. So of course, you can also write this in a polar form. You can write it in a polar form, which is going to be that, and then you can have cos minus pi over 4 plus I sine minus pi over 4. Can write it as well in a polar form. So one needs to understand how to go from polar to exponential or and then backwards as well. Then the 18, we're asked to find again to write this complex number to compute the real and imaginary parts of this complex number I minus 4 over 2I minus 3. It's really not tricky. If you look at the denominator, 2I minus 3, you want to write a complex conjugate of this. So you need to be a bit careful and write this as minus 3 plus 2I, right? Minus 3 plus 2I. So that its conjugate now will become minus 3 minus 2I. Okay, so that's the only trick you need to use here to be able to get the right answer. So here you need to use this conjugate, then you multiply by the numerator and the denominator, you expand. So if you multiply here, I minus 4 times minus 2I minus 3. If you multiply, you have I minus 2I, which is minus 2I squared. Then you have minus 3I plus 8I plus 12 all over 13. Then this is equal to, this is then equal to 2 plus 5I plus 12 over 13, and it is equal to 14. So it is equal to 14 plus 5I over 13. And now we have the real part and then the imaginary part given. Then the final one was to write, to demonstrate your ideas on rational number understanding. So we have Z1 to be A over B. Of course, in that sense, I wrote Z1 to be A comma B. I wrote Z2 as well to be C comma D. And then I wrote Z3 is equal to E comma F. But of course, we know A comma B to be the same as A over B, and then Z2 is C over D, Z3 is E over F. And so the question was to solve 6 over Z2 plus 1 over Z1 plus Z3 squared. So 6 over Z2 is 6D over C, and Z1 plus Z3 squared was equal to A squared F squared plus E squared B squared plus 2AF EB over B squared F squared. And then if you then put it together, you'll be able to arrive at this solution here. But of course, already we can write C into brackets A squared F squared plus E squared B squared plus 2AF EB. And then here we have 6, 6D, we have 6D, and here we have A squared F squared plus E squared B squared plus 2AF EB. Then plus CB squared F squared. Then we can write it again in terms of our normal notations for rational numbers. So This ends the solution set for page 2.